Today we will be talking about power series and analytic functions. The challenge for today is to think about whether there are cases in which we can solve an ordinary differential equation with non-constant coefficients. For example, this form of the Aries equation, which by the way has applications in optics and probability and other areas, is a second order linear homogeneous differential equation, which are all good things, but it is not constant coefficient. By our existence and uniqueness theorem, we do know that there exist two linearly independent solutions to this equation. And those two linearly independent solutions are going to exist on the entire real line because the coefficients of our ODE are in fact continuous on the entire real line. The challenge, however, is that we actually don't have a way of solving an equation that looks as innocuous and almost simple as an equation like this, precisely because of the non-constant coefficient. So let's just remember what we do have available to us so far. If we're in the world of first-order ordinary differential equations, we split those into separable differential equations and linear differential equations, two categories that can overlap. If the equation is separable, you can solve with separation of variables. And if the ODE is linear, you can solve with an integrating factor. Now, in the world of second order ordinary differential equations, we learned some other techniques. Within that world, we can also have linear differential equations. Within the world of linear differential equations, we can ask if they are homogeneous. And overlapping both of those, we have constant coefficient equations. The techniques we have available to us so far include, if we are in this intersection of linear, homogeneous, and constant coefficient equations, we can use the characteristic polynomial approach. We've also learned that if we are not homogeneous, but still linear and constant coefficient, we have a couple of approaches available to us, and those are variation of parameters and undetermined coefficients. What we'll be looking at today is this special case here, where we are still linear and homogeneous, but our coefficients may not be constant. There is a subset of non-constant coefficients that we have one way of dealing with, and that is if our coefficients are polynomial. Of course, outside of all of these, we can implement numerical methods when we don't have anything else available to us, or in order to enhance what we do know about what's available to us. Okay, so previously we learned that the general second order linear undriven differential equation of this form cannot be solved analytically if those coefficient functions are just arbitrary functions. It does turn out, though, that we do have one way of getting some insight into the behavior of the solutions to these differential equations if the coefficients are simple polynomials. In that case, we can employ power series solution methods to make some progress on looking at how solutions might be behaving. Today, we're going to look at building up tools around power series and analytic functions. And in particular, the methods that we're looking at are around ordinary points. And basically just what that means is we are not dealing with places where we have asymptotes or we risk dividing by zero. Next time, we are going to talk about power series around singular points, where these points can be a little bit trickier. Let's go to the next page. Here we've provided a brief background on power series. You don't have to know everything in detail. You just need to get a pretty good idea. This is basically a list of definitions and vocabulary. So a power series is an infinite series of polynomial terms of the following form. The coefficients, these a sub naught, a sub 1, a sub 2, and so forth, are often referred to more generally with a subscript n or I. So the a sub n's or a sub i's are the coefficients, and the x naught is the center of the power series. So when we talk about expanding about a point, that is what we mean. We mean making x naught the point of expansion. Now, as with any infinite sum, the series can converge or diverge, and don't worry, we're not going to get too much into figuring out how to test convergence or divergence. For that, we need to go to a different class. But we do need to be aware of the issues of convergence and divergence. In this case, we should be aware that power series have an interval of convergence that typically looks something like this. In other words, about our point of expansion, x naught, there will be a range of radius r in which the power series will be able to converge. And that is called the radius of convergence. Now, a Taylor series is a particular case of a power series. In the case of a Taylor series, the coefficients relate to the function's derivatives at that point of expansion. This is the formula for a Taylor series, which many of you may have already seen in calculus. Again, the center of this power series x naught is our point of expansion. Now, some of the ways in which we are going to be using Taylor series in this class include being able to look at a truncated version of the Taylor approximation, which will end up just being a polynomial that gives us a pretty good approximation to the function that we're looking for, basically the solution, near the point of expansion. In fact, Euler's method that we talked about earlier is an application of a linear Taylor approximation to the solution function. These power series can also help us solve certain differential equations, as we will see. What I do want you to take away from this is that there are some very common Taylor series that are good to get used to recognizing. In particular, the series for e to the x, expanded about x equals 0, the series for sine x, again about x equals 0, cosine x about x equals 0, the series for 1 over 1 minus x about x equals 0, and the series for natural log of x about x equals 1. Keep the forms of these series in mind, and notice that the radius of convergence is the entire real line in the cases of e to the x, sine x, and cosine x, whereas the radius of convergence for the last two functions, 1 over 1 minus x and natural log x, is limited to either the absolute value of x being strictly less than 1 or the absolute value of x minus 1 being strictly less than 1. Let's go to the next page. Now, how are power series connected to what we want to do with our differential equations? We sometimes can replace a complicated function with a power series, since polynomials are easy to deal with. So here again is what a typical power series looks like. An expansion about the point x naught. This is our summation of polynomial terms. And as I said before, x naught is the point of expansion or the base point. Now, in the special case where x naught is 0, and this happens very often, then the power series collapses to something that looks like this. Now, here's the big idea. If the general second order linear undriven differential equation of this form cannot be solved analytically, but those non-constant coefficients are polynomials, then a power series, which basically is a large polynomial sum, might actually be helpful in figuring out how to solve that differential equation. Now, later we're going to see why linearity is crucial for this to work. In practice, it is not very easy to graph a function that is written as an infinite sum, but what generally happens is we truncate that sum so that we have what looks like a normal polynomial, not something infinite, and we can get a pretty good approximation to the solution that is accurate, very close to our point of expansion. Let's go to the next page. So a few more background details. We already discussed the fact that power series can converge or diverge, and that they will converge within that radius of convergence. Since we're going to be working with differential equations, we're going to need to be able to differentiate a power series. So what allows us to do that? Because remember, when we're dealing with the world of the infinite, we have to be very careful not to do things that we comfortably do when objects are finite, because things can actually go wrong. So when can we treat this infinite series almost like a regular polynomial? We have to define what it means to be analytic around that point. A function is analytic if there are coefficients that allow us to write that function precisely as an infinite sum. So notice this equal sign is really important. The function is identically equal to that infinite sum, not just approximated by that sum. And this sum clearly has to converge within the radius of convergence. If our function is analytic, in other words, if it has some convergent power series representation, then f is going to be analytic not just at the point of expansion, but actually for all points within that radius or that interval of convergence. Now, why is analyticity important? Inside the radius of convergence, we get to treat that infinite series like it's a regular polynomial. So we can differentiate or integrate the power series term by term as much as we like and retain a true statement. Consider, for example, the power series for sine x about x equals 0. Differentiate term by term, and you actually get the power series for cosine x about x equals 0. So just to reemphasize, when we are dealing with infinity, standard arithmetic rules don't always apply, but if the functions are analytic, they will behave as we would expect. Note that analytic functions are infinitely differentiable, and if you want to know more details, take a real analysis or a complex analysis course. Let's go to the next page and look at our first example. Here we come back to this example of an Aries ODE, the solution of which is an Aries function. Now, before we begin, let's think about what it means for the behavior of these solutions to be described by a differential equation whose coefficient is not constant. What happens when we look at the behavior of the differential equation around x being about -5? This differential equation is going to behave something like y double prime plus 5y equals 0, which, as we know, has oscillating solutions of the form cosine and sine. On the other hand, if we look at what the solutions are going to behave like around x equals +5, we can approximate the differential equation by y double prime minus 5y. And that is going to have exponential growth and decay solutions. Therefore, as x changes from positive to negative, the behavior of the solution is going to change from oscillatory to exponential. Now, as to where the point of expansion should be, it is usually going to have to match where the boundary or initial conditions are placed. So if we have an initial condition or boundary condition y of 0 is 1 and y prime of 0 is 0, we are expanding about 0. So we are going to choose x naught, our point of expansion or our base point, to be the point about which we expand our power series. So let's assume that our solution y has a power series expansion representation about x naught equals 0. How are we going to make use of this power series? Of course, we are assuming that the power series expansion is for a function that is analytic, so we can differentiate term by term. Writing out our solution as power series in long form, we have a naught plus a1x plus a2x squared and so forth. And in summation form, we can write this as the sum as n goes from 0 to infinity of a sub n x to the n. Now, let's differentiate term by term in order to find out what the power series for y prime will be. Of course, the constant term goes to 0, and each term is just a differentiation of the term above it. And we can also write this series in summation form. This becomes n equals 1 to infinity n a sub n x to the n minus 1. All right, pause the video and just take a second to work out y double prime. What I hope you were able to get is the following. The sum as n goes from 2 to infinity of n times n minus 1, a sub n x to the n minus 2. Now note, I changed the start point for each one of these sums from n equals 0 to n equals 1 to n equals 2, but I could actually start each one of these at n equals 0 if I so chose, and I would simply be adding on 0 terms to my sum. So if it's convenient to start everything at n equals 0, that is also possible. Now, how should we go about finding the values for the coefficients a1, a2, and so forth? We already know a couple of things. If I look at y at 0, from the series itself, I know that plugging in x equals 0 gives me y of 0 must be a naught. From the boundary conditions, I know that y of 0 has to be 1. Remember, our boundary condition was right up here. Remember also that we have a second boundary condition, y prime of 0 is 0. So similarly, from the series, I know that y prime of 0 is going to be a1. And from the boundary condition, y prime of 0 has to be 0. In this way, I have already determined values for a0 and a1. Let's go to the next page and continue with the process. We've already found the first two coefficients, a0 and a1, from the boundary conditions. And in order to find the remainder of the coefficients a sub n, we simply plug into the differential equation and solve. The process goes something like this. Our differential equation is y double prime minus x times y equals 0. Plugging in the second derivative of our power series, we have y double prime is the series n equals 2 to infinity, n times n minus 1, a sub n, x to the n minus 2, which we figured out on the previous page, minus x, which is not part of the power series, it's our coefficient, times the series for y, which is n equals 0 to infinity, a sub n x to the n. That all gets set to 0. We can now write these out in long form in cluster terms. First, I will pull the x inside the second series. Now, what does this tell us? Here is the key. This equation has to be true for all values of x because the power series is supposed to be the solution of our differential equation. Now, the only way for the left-hand side of our equation to be equal to 0, as it is on the right, is for every coefficient of every power to be set equal to 0. So pause for a second and think about why that would be. Here's the reasoning. Why does every coefficient have to be 0? The set of functions that we are summing together is a linearly independent set. And so if we are going to sum these functions and make that sum be 0, the only way to do that with a linearly independent set of functions is to force every coefficient to be 0. That is our definition of linear independence. Okay, so let's look at each individual coefficient in the sum. The first thing we have is the term that does not have an x with it. So it is the constant term. If this is going to have a hope of summing to 0, then our constant term has to be set equal to 0. So the coefficient of x to the 0 formally is 2a sub 2, and that has to be 0, which of course means that I now have a value for a sub 2, which is 0. Let's look at the next one. The coefficients in front of the x term are 6a3 and minus a0. The 6a3 minus a0, that has to be 0, which requires a3 to be a0 over 6, which is going to be 1 over 6, because we already know that a0 is 1. Finally, let's look at the x squared term. We've got a 12a4 and a minus a1 in front of our x squared term. So that means that the coefficient of x squared has to be 0, and that allows us to solve for a4, which has to be a1 over 12, which is going to be 0, again, from the boundary conditions. So far then, we have the first few terms of our series. And so we can see that our solution to the differential equation, y sub x, is going to start off looking like 1 plus 1/6 x cubed plus something else, and we're going to have to keep working to find out what happens next. So we can keep working on the coefficients one by one, or we can try looking for more general patterns, which we'll do together in class. But first, let's go to the next page. On this page, I want us to be able to visualize what it means to look at a truncated power series approximation. In blue here, we have the exact solution to the differential equation we've been looking at. What we have in orange is that first approximation that we just worked out on the previous page. 1 plus x cubed over 6. Those are the first two terms in our power series. We can see right around here, around x being 0, our point of expansion, the match between our cubic approximation and the exact solution is actually not too bad. It's pretty good near x equals 0. If we look at the next figure, I've now plotted on top of this a couple more polynomials where we've extended out our series solution a couple more terms. So one more term gives us this 6-degree polynomial where we also are matching right around this area near x equals 0 and maybe matching a little bit better. And then we get yet one more term, this 9th-degree polynomial, where our match maybe extends even a little bit further, a few more values of x around x equals 0. So what we're seeing is that the solution improves with each additional term in the power series that we add. So we can see here that even though we don't go out to an infinite number of terms, the truncated power series is going to give us a reasonably good approximate solution near our base point or our point of expansion. And what we see here is an actual plot of two of the area functions. Remember that there should be two linearly independent solutions. You can read more here. And what I want to point out is right around x equals 0 is where we begin to see a change of behavior as we talked about toward the beginning. So when x is greater than 0, we're going to see exponential behavior. And when x is less than 0, we see oscillatory behavior. The formal names for the area functions are a sub I and b sub I. And again, you can look up more about that online if you wish. Let's go to the next page. Remember, I mentioned earlier that it's really important that the differential equations we work with are going to be linear. Why? Here's an example of how it's not useful to use power series solutions if you happen to have a non-linear equation. Can you see here where the non-linearity is in this ODE? It's right here. Y times y prime. So let's try the approach we were talking about before. Take y as a power series and its derivative and its second derivative, and let's plug it into the differential equation. Plugging it in gives us something that looks like this. And now we're going to try to look at the coefficients one at a time. What will the constant term or the coefficient of the x to the 0 term be? We would get a relationship that says that 2a2 plus a naught a1 needs to equal 1. For the coefficient of x1, we're going to get 6a3 plus 2a naught a2 plus a1 squared equals 0. And we'll do one more. For the coefficient of x squared, we get 12 a sub 4 plus 3 a naught a3 plus 3 a1 a2 equals 0. So right here, what we're being asked to do then is to find solutions for a naught, a1, a2, a3, and a4 from this non-linear set of equations, which is not necessarily going to be straightforward. So the issue is that nonlinear differential equations produce nonlinear equations for the coefficients, and those are very difficult to solve. In addition, the product of two infinite series is going to be a huge headache. And so if we've got nonlinearities, that's going to make things even worse. So this is why power series methods typically are not going to be used for nonlinear differential equations. All right, in class, we are going to get to practice a lot more. So I will look forward to seeing you then. Bye.